About section 3.1 of the book, the measures of central tendency, and also section 3.2, working with standard deviations. First of all, we're going to talk about what is a statistic. Now, a statistic is a characteristic or measure obtained by using data. A characteristic or measure obtained by using the data. That would be a statistic. Now, a parameter would be a characteristic or measure obtained by using all of the data. And so when we create parameters, it's based on all the different statistics. And that's what we're going to do today when we look at the measures of central tendency. We're going to look at numbers that kind of make a middle, and I don't want to peg this as being the median, but it's going to be a middle-ish number. Now that's kind of an Anderson original here, because we're going to look for numbers that have kind of the center of the data. So there's a lot of different ways to talk about the center of the data. For example, we have mean, which is an average. And the average is made when you take all of the numbers. So take all of the numbers, add them up, and then divide by the total. And there's a lot of notation to go along with this. For example, you can use the Greek symbol sigma to mean to add up all the numbers in your list and then divide by the total, or the count, as designated by the letter N. And this will be another way to talk about averages. Averages, X bar, for example, is a way to say average. And if you want to talk about population, you can use the Greek letter mu. And mu is when you do the average of a population sample. Now, one of the examples I want to give you is just pretty simple. Just if I have the numbers 3, 4, 5, 8, 9, and 11, you add these up, you total them up, and when you get your total, you're going to divide that total by 6. If you do this correctly on the calculator, you get a decimal of 6.6 repeating. According to the rounding rules in the book, they want you to go one decimal beyond what the data set had. And since this data set had no decimals, we're going to go one decimal beyond that. 6.7 is that example. Now, common mistake. A lot of times when people type in averages, they don't total the numbers on their calculator before they do their division. So what happens is they get this. They type in all the numbers to add up and then go divide by 6. Unfortunately, what that does, it only divides the 11 and the 6. It doesn't divide the entire set by 6. So if you do this, you'll notice your answer will be actually greater than the 11 in this case, and that will mean that that's definitely not the average. The average has to be the balancing point between these numbers, and the balancing point is 6.7. The median is also known as the middle. And that's why when I said middle-ish number, I didn't want you to think that the measure of central tendency is always the median. But I prefer medians. Medians are not affected by outliers. And what you have to do first is to put the numbers in order. And here's where you might want to pause the video. After you've downloaded the worksheet, you can practice finding the middles yourself. And then unpause it to see the answers. The middle of this data is between 5 and 7, so that's 6. The middle of this data is between 7 and 7, which is 7. The middle of this data is between 10 and 17. Now, instead of writing out all the numbers, it's best when you have a large gap between two numbers. You go 10 plus 17, and then divide it by 2. Finding the average of the two numbers will easily find your middle, which is 13.5. And then for D, you may think that the median is 7 and 7, but I have not put the numbers in order, which you need to do, and the number between 7 and 8 is 7.5. Now we're going to go to mode. Mode means in the fashion. And mode is another way of meaning most popular. So whatever choice comes up the most is going to be our mode. Now, what we're going to look at is we're going to look at each set of data here. You'll notice that there is no number in data set A that's repeated. So this would be an example of no mode. Don't put down 0 mode, because 0 mode would then indicate that the number 0 has come up the most. So no mode is the acceptable way to report that. Here you'll notice you have 2 6s and 3 7s. This is an example where you only pick the number that showed up the most. Even though there are 2 6s, since 7 came up the most, 7 is the mode. And this is a unimodal example, which means that there is one winner and dataset B has one mode. Now let's take a look at dataset C. Dataset C has 2 10s and 2 17s. This is bimodal because it has 2 modes in it. A tie, and that would be dataset C. Now you're wondering, well, dataset B has 2 modes, but technically since 7 came out ahead with more 7s than 6s, this is not considered part of a mode. Now for dataset D, you'll notice there are 3 7s and 3 8. This is another example of a bimodal situation where they are tied with 3 apiece. Now multimodal would be is if you have a data set with greater than 2 modes in it, and I don't have one on this worksheet, but that would be called multimodal or greater than 2. Midrange. The midrange data right here is going to be, it's not used too often, but it's when you take your highest number, subtract your lowest number, which will give you a range, and divide that by 2. So it's basically finding the median of your maximum and minimum. I personally am not a big fan of the mid-range because it really takes the outliers and gives them a lot of weight. Now, we're going to talk about shapes of distributions before we get to standard deviation, because there are 3 different types of distribution shapes. We've got symmetric, we've got skewed to the right, and we also have skewed to the left. Now, if you want to take a look at what that would look like maybe on a histogram, I've got some pictures there. There's an example of a standard deviation. Now, this is important because we can use standard deviation for normal sets of data. But as soon as we get to skewed data that's skewed right or skewed left, then we're pretty much going to try to lean on box and whisker plots to look at the variation. So with that segue, we're going to get into standard deviations. The standard deviation is the building block of a lot of the work in this book. You got to start out first with the normal curve. The normal curve has an average in the dead set in the middle, right there. There's your average. Now, there's a standard deviation that's units away from the average. We call this one standard deviation away from the norm, and this is also one standard deviation away from the norm below it. Now, this data right here holds 2/3 of the data. So if you have a population of people, between one standard deviation above and below the norm is 2/3. So roughly 66.6%, or 66.7% if you rounded, is between one standard deviation above and below the norm. And what we're going to do today is figure out with a set of data what is considered normal above and below one standard deviation. So we're going to find the actual number of S. And if you want to think about, let's say, IQ, hypothetically speaking, if the average IQ in America is 100, then this might be 120 and this would be 80. So 66% of the population would be between 80 and 120. Now again, I'm making that up, hypothetically speaking. You can also go another standard deviation away, Let's say we went from hypothetically 120 to 140, and we went down from 80 to 60. The second standard deviation away obviously would be a very small portion of the population. The top 5% would be higher than the second standard deviation, and the bottom 5% would be lower than the second standard deviation. So you'll notice that these groups, even though they are equally spaced apart, do not hold the same amount of data, or the same amount of the people right there. This is 5%, this is 2/3, then you can do your calculations to figure out how much percent is here and here. But roughly, each tail, and we call these above one standard deviation a tail, is 1/6 of the data, or 16.6%. And go down that way, 16.6%. All right, so it's time to start looking at the data. Just put these, before we start that, one standard deviation to the left or the right of the average is 2/3 of the data, and each tail holds 1/6 of the data to make 100% of all the data or population. Now what I've done for our first example, and you can actually go into your calculator, and I'll show you at the end of the video how to do this. I will show you how to compute a standard deviation by hand. The calculator can do this very quickly, but it's nice to see where this comes from. The first step is you have to find your average of these video game systems. I picked some video game systems from the Best Buy catalog at random, and I listed them here. Now, when I add all these up and divide by 7, I get a sum of 250. So my sigma x divided by 7 is going to give me 250. That's the average price. Now to save time, I can put my 250s right here, or just draw an arrow. Then what I'm going to do is find my deviation from the mean, which is going to be my absolute value, the distance between here and here. And that's going to be 0, that's going to be 100. The distance between that $150 Nintendo Wii and the $250 average price is $100. Above or below, you're always going to put the positive value there, because these are technically absolute values, which always takes the positive distance. This is going to be 100. This is going to be 150. The distance between 500 and 250 is 250 as well. And this is going to be 200 and 250. And this is going to be 50. And then 150 again to go from 100 to 250. So once we found that distance, we're now going to go to the squared deviation. And we take each of our little numbers here and we square it. 0 times 0 is 0. 100 times 100 is 10,000. And I'll notice I have that again. 150 times 150, or 150 squared, is going to be 22,500. And I notice I have that again down here at the bottom, so I'll just copy it in there. 250 squared is 62,500. And 50 squared is 2,500. All right. Now we're going to add all of these up. If we add all these up, you get 130,000. Then we are going to take that 130,000 and divide the sum by n minus 1. So we're going to take the 130,000, and it's really laid out in the book why we do n minus 1, but the easiest way to think about it is to try to throw away one of the weird items, or throw away, if you were taking tests, for example, you would throw out your worst test, or you throw out an outlier, the one piece of data. So we're going to say, instead of dividing by 7 like we did on our average, we're going to divide by 1 less, which is 6. Which makes a big difference if you have a small set of data, but in a very, very large set of data, taking away one thing is not going to make a huge difference. So 130,000 divided by 6, if you get that, we're going to go to 21,666.7. And I'll go one decimal beyond because of our boundaries, and we call this the variance. Then we take the square root of the variance, so the square root of 21,666.7, and we get an answer of 147.2. And this is our standard deviation. Our standard deviation is created by the square root of the variance. Now, we get to make the picture. And this will bring everything together, unlike the abstract percentages up at the top of the screen, or the top of the worksheet here. You can see how this is built. This is my average, and this is going to be 250. That's my average price of the video game systems. One standard deviation above and below. So we take our $147.20 and we go to 397.2. That's 147 above. We subtract the 147, 102.80, and that would be the price of one standard deviation away here and here. Let's go with second standard deviation. So then we go to 544.40. And then we go down to the very bottom down here, which is negative $43.40, which doesn't make sense practically, because if we're taking $147.28 away from this value right there, you would see that that doesn't quite make any sense. All right, so with that in mind, we've gotten our curve here, and what this tells me is that 66% of the video games are between these two, and they would be considered more than one standard deviation away from the norm by going beyond this. So there was some weird systems over here in this range, and there was actually only one system that was below here, and that was the PlayStation 2 at the time that I received this data. Now there is a range rule of thumb, and the range rule of thumb means that if you want to find your standard deviation, you'll take your range, divide it by 4, and that gives you your standard deviation. Now in this case, our maximum was 500 and our minimum was 100. If you divide that by 4, or 400 divided by 4, you get an answer of approximately 100. Now that isn't a very good statistic to compare these two, but you'll find on the page that we're going to do next, on the back one, you'll see that there is a lot of similarity between the range rule of thumb and taking the square root, or to get your standard deviation. So these two aren't very far here, but they will be a lot closer on the next page. Now, to speed things up a little bit here, you've downloaded this document through my Moodle page or from your other instructor. I will tell you straight up that the average is 80. So the average is 80, and then you should pause the video and you should try to compute this all by yourself. When you unpause it, I'm going to have the answers for you so you can check your work. All right. Now that you've finished the problem, here's what it looks like. Okay, you have a lot of deviations are 0 because she earned 80% on a lot of her homework scores. So there's a lot of similarities here. Then you do your standard deviations, and you'll notice that there really isn't a lot. Even though there are 20 pieces of data, there isn't a lot to add up because a lot of these deviations are 0 when squared. Then you take your 1600 divided by 19, not 20, and this gives you a variance of 84.2. Take the square root of 84.2, and this gives you an S, or standard deviation, of 9.2. So if we look at her on the curve, it looks like she has an average of 80. She has 66% of her scores are between 70 and 89.2, and you'll notice that only 5% of her scores would actually be bigger than this on this standard deviation. Now, if we did the range rule of thumb, we would take her maximum, which is 100, minus the minimum, and her minimum in this case would be a 60, and we would divide that by 4. That's the range rule of thumb there. And you would see that this answer, once you actually do it, is going to give you a very, very close answer to 9.2. Let me grab my calc to do that, because my next part of the problem is to show you how to do all of this on the calculator. So 100 minus 60 divided by 4. You can see that right there. This range rule of thumb came out embarrassingly close to the square root of the variance, or the standard deviation. Now, if you have a graphing calculator, the best way to do the standard deviation is to type it into your stats. Now, get to a clear screen, and I'm going to reset my calculator just so I don't have anything affecting it. So get it to a clear screen first, and then go to the stat key. The stat key is located under delete, and hit enter. Now we're going to type everything into list 1. Make sure that says L1 at the top. And then type in your scores. Just like you would type into a spreadsheet on Excel, this will be the best portable way to do your standard deviation. Okay. Alright, now I've typed in my data. It looks like I might have missed one though. Yep, need one more 90. Okay, now if I didn't type in any number incorrectly, I should be able to do this command and it should work out fine. Hit the stat key once, then the right arrow key, and then the number 1 key, and then enter. And this gives you an average. It also gives you the sum. It gives you sums, and the most important thing that you want to look at right here is notice that the standard deviation is right there, 9.2. And if you scroll down, you can actually get some numbers that will help you on the next lesson's box and whisker plot. Alright, now with that in mind, I want to tell you one more thing about this problem, or about this worksheet. And this is something called the coefficient of variation, otherwise known as CVAR, or C sub var if you're using a word processor. What this lets you do is it lets you compare standard deviations. Lets you compare them. Now, the formula for this coefficient of variation is to take your standard deviation and divide it by your average. So let's take a look at the video game systems. Okay, so the gaming systems. We had found our standard deviation was about $147.20, and we're dividing that by the average price of $250, which gives you 0.588, or 59%. Then we're going to take a look at grades, the grades of Susan, and Susan had 9.2 standard deviation over an average of 80, which is 0.115, or 115 thousandths, which is roundable to 12%. What this means is that if you compare the video game systems versus the grades, Susan was a lot more consistent than the video game systems were. The video game systems had a lot more variation, and so that coefficient of variation was bigger. And the coefficient of variation for Susan is smaller. Now granted, this is comparing extreme apples and oranges together, but it just talks about how varied the systems were. Alright, thank you for watching. If you have any questions, please send me an email, or through the Moodle page or through the KCC website.